My name is Ashley Kane, and this is my presentation for Physics 2212 of Lab 4 about circuits and capacitors. The intention for this lab is to predict circuit behaviors and values for the measurements of current and potential differences over time in those circuits that contain resistors and capacitors in series and parallel organization. Some important physics principles to understand for this lab are Kirchhoff's loop rule, which means that the sum of the electric potential around the circuit is zero, and this includes the conservation of energy. The node rule, which means that the sum of the currents flowing into a node is equal to the sum of those flowing out of it. Ohm's law, which is that the drop in voltage across a resistor is proportional to current times resistance, and the capacitance formula, which is C equals charge over the change in potential difference. Also, we need to understand the equivalent resistance in different setups of circuits. So in series, it's that the equivalent resistance is equal to the sum of all the internal resistances. In parallel, 1 over the equivalent resistance is equal to the sum of 1 over all of the internal resistances. Our first experiment in this lab was to observe charge and energy conservation in a series circuit. For this circuit, we set up two 1.5 volt batteries, two ammeters, one 47 ohm resistor, one 100 ohm resistor, all in a series circuit. Then I predicted what the current would be flowing through ammeter 1 and 2, and these calculations are on the right, and I found that to be 0.02 amps. I created a current simulation for this series circuit and found that the ammeter read 0.02 amps, which is the same as my prediction. And when you place ammeters in a backwards direction, the reading does not change. Next, we were asked to replace one of these ammeters with a voltmeter, shown at the bottom, and record what the ammeter read. So the ammeter read 0 amps because current doesn't flow since the circuit is open at the location of the voltmeter. The voltmeter read 3 volts, which is equal to the potential difference across the battery. If the loop is complete, the total change in potential difference would be 0 volts across the entire circuit. Next, we were asked to reclose the circuit with 1 ammeter and record the potential difference at different points with a voltmeter, shown in the diagram in the center. These recordings are noted in the bottom left, the significant recordings being from A to B, 3 volts, from C to D, 0.959 volts, and E to F, 2.041 volts. When adding the sum of the potential differences, because of conservation of energy, these should all add up to be 0, and this is shown in the following equation, which is that the potential difference is equal to 3 minus 0.959 minus 2.041, which is equal to 0 volts, and these results are also shown in the graph at the bottom of the screen. Next, we were asked to observe the changes in readings, given that we're placing different components in parallel with other ones. First, we placed the voltmeter in parallel with the ammeter and noted that the ammeter reading does not change, and the reason for this is because voltmeters have infinite resistance, so no current will choose to pass through them, and therefore all the current will choose to continue to pass through the ammeter and the reading will not change. Next, we added an ammeter in parallel with R2, which has a resistance of 100 ohms, and at this point both ammeters read 0.06 amps because the current in the parallel configuration will choose to all flow through the ammeter because it has 0 resistance. So now there's only 47 ohms of resistance acting on the current, and recalculating the new current, we found it to be 0.063 amps, which is similar to the reading shown in the simulation. In this section, I found all the equivalent resistances of each of the components in the circuit. In this experiment, we observed RC circuits. We placed a 9-volt battery, a 10 ohm resistance bulb, and a 200 millifarad capacitor in series. Over time, we saw that when the capacitor is being charged, the bulb dims and eventually is no longer lit. The current in this situation also flows in a clockwise direction. After disconnecting the battery and only having the bulb connected to the charged capacitor, the current reverses and the bulb is lit but slowly dims as well. When observing the time to charge a 10 ohm bulb versus a 20 ohm bulb, it was shown that the second bulb has a larger resistance, so the time to charge and discharge will double with the doubled resistance. Recreating this experiment with a 30 ohm bulb, we observed the voltage versus time graphs of the charging and discharging capacitor. When charging the capacitor, the initial voltage across the capacitor was 0 volts, but after t reaches infinity, it is equal to 9 volts. In estimating the RC value, you would do 0.2 times 30, which would equal to 6 seconds. In the next section, we're going to graph the natural log of the change in potential difference over the change in initial potential difference versus time. And this section shows that the slope of this graph is going to be equal to -1 over RC. Here are some of the values that I recorded while discharging the capacitor, and the slope of the graph created by these values was -0.15, and when reciprocated and multiplied by -1 was equal to 6.67 seconds, which is similar to the theoretical value calculated, that was 6 seconds. Here are our conclusion questions. So the first one was, what if we use an actual capacitor, an actual ammeter instead of an ideal simulated one? And a real ammeter wouldn't have zero resistance like the simulated one, so the overall reading for the current in the circuit would be lower than the ideally measured one, since the current is inversely proportional to the resistance, which would be higher with the real ammeter. If we had used a real battery to charge a real capacitor with no resistance, or with no resistor, to maintain Kirchhoff's loop rule, the only drop in voltage would occur across the capacitor, and the capacitor would be charged as soon as it was connected. In real life, since the wires and other components would have some resistance, there would be greater than 0 seconds taken to charge the capacitor, but this value would still be close to 0.